Hello all, welcome back to Unit 5. Today we'll be looking into magnets and electromagnetic induction. In magnets, we'll analyze the dipole nature of the magnets, the two poles, and the field around it, magnetic field around it. Then we'll look into the induction processes, the electromagnetic induction, and how that process leads to uh, induced EMF in the coils and hence induced current in the coils. Basically, we'll look into how current is produced in a factory or in a hydropower plant or nuclear power plant or the coal power plant. So we'll look into electromagnet, generator, transformers, their basic working principle by means of some of these simulations. So this is the basics of magnet. Uh, every magnet has two poles, North Pole and South Pole. We can visualize them as electric charges and electric field. Uh, as there are two poles, there are two electric charges, positive and negative. The electric field lines go from positive to negative. um, or if you just have positive charge, you can have field lines emanating outward from the positive charge, or just negative charge where the field lines are going towards the negative charge. If you bring them close together, they act like a dipole, and the field line originates at the positive and ends at the negative. Similar scenario here in the magnetism. You can bring um, two poles of a magnet together and you'll see magnetic field lines originating at the North Pole and ending at the South Pole. However, the main difference is we can have a single positive charge, and charge can just start at the charge and emanate outward to infinity. In terms of magnets, there is no single pole, and hence all electric field lines that starts at North Pole meets eventually end up in the South Pole. And just even the looking at the bar magnet itself, you know it the magnetic field lines will continue inside of the magnet and always form a loop. Okay, so magnetic field lines always form a loop. However, mm, that's not the case for the electric charges. And in the similar to charges, the same poles repel each other. The magnetic field lines would look like this, and the opposite poles attract each other. Um, and our Earth acts like a giant magnet. If you suspend a magnet, it always end up pointing to north and south. So in short, magnets have magnetic fields around it. These are permanent magnets. The other types of magnets are electromagnet. Those substance act as a magnet only when there is current around it. Um, so there is also another way to create magnetic field by simply passing current through a wire. uh, it it generates these concentric circles of magnetic field, and these magnetic field uh, instantly starts to move out. So if you turn on the current at one instant, the magnetic field starts to generate, and these field lines travel outward, and their speed is dictated by mu naught, called the magnetic constant. And these field lines emanate outward, um, and so these blue concentric circle here are the magnetic field lines. So again, this is simply a conductor carrying current, so we don't need a magnet to have magnetic field. Okay, any current carrying wire produces magnetic field around it. So we'll explore all these things as we go. The next thing we need to understand is the magnetic flux. So now we know what magnetic field is, field lines are. If we pass those magnetic field lines through a certain area, we get flux. So the magnetic flux is magnetic field strength times the area of that loop. How much magnetic field lines passes through that loop, and that loop can be circle or a rectangle or a square or any other shape. Uh, that the product of the field and the area gives us the magnetic flux. And this magnetic flux depends on two things, as you can see from the formula. It's the dot product of the two vectors. Magnetic field is a vector, area is a vector here, and the dot product, we can write as the magnitude of each BA, and dot product takes the cosine term at the end, and phi B, phi is a symbol for magnetic flux, actually phi B. For electric flux, it would be phi E. So phi B magnetic flux is BA cosine theta. So from this relation, we can see that strength of magnetic flux depends on the strength of magnetic field, B, the area of the loop, and the angle between the area vector and the magnetic field vector. Okay, and what this means is we can increase the flux by either increasing magnetic field or by increasing the area. Larger area means more flux going through the loop, hence more flux, and the cosine theta of these two vectors, meaning if the field vector, magnetic field vector, and the area vector are aligned, meaning theta is 0, right? Both align. Theta 0 means cosine 0 is 1. So we get the maximum flux when the field, magnetic field, aligns with the area vector A, right? So that simply means all of the magnetic fields are going parallel to area vector A, means all of the um, magnetic field lines are entering horizontally through this vertical circle, we get the maximum flux. Now, if like in the bottom case here, this is again a loop. All of the magnetic field lines go perpendicularly upward, we get the maximum flux. If you incline this magnet or the magnetic field at some other angle, then your theta becomes greater than 0. As theta increases, then cosine 0 is the maximum. Any other values gets starts to reduce, hence flux reduces. And again, the changing magnetic flux, and we can change that magnetic flux by changing three things. Either we can change the magnetic field, area, or the angle, and that creates an EMF, and which is called the Faraday's law. And what Faraday said is, Faraday actually experimentally demonstrated these things. Michael Faraday, one of the best experimentalists in physics, he never went to school. He worked in a lab for some other physicist, and he learned from them just doing experiment. He had no mathematical knowledge whatsoever, and based on his experiments, he concluded that whenever the magnetic flux, which is phi b, changes in a loop, then that change in magnetic flux induces EMF, or the voltage in a wire, like this wire over here. And first he found that when the flux is constant, when the flux is not moving, meaning if this magnet was not moving and it was there stable, the magnetic field was constant, and that was not inducing any EMF or current in the wire, and the emitter reading was 0. But whenever the magnet is moved up or down, you know, so that's why it is the rate of change of flux. As the magnet was moved up and down, the flux would change, magnetic flux going through the loop would change, and that would induce EMF in the wire. And he devised this formula, or and or his experiment led to this formula saying induced EMF is um, rate of change of flux, and that n is there for number of turns. It was also found that if you have a large number of turns, the wires, then the induced EMF would be increased by factor of that n value. And since currents and EMFs created in this manner are called the induced EMF or the induced current. And so here's a proper way to calculate EMF. This is a general formula. That's change in flux versus change in time, basically. And this we can rewrite that as n times flux, final flux minus the initial flux divided by the delta t. For example, when this magnet is down here, we can say that the initial flux through the magnetic loop is 0, no flux passing through the loop, and let's say it takes 1 second to move the bar magnet up here. Then in that time frame, so delta t is 1 second, and we can calculate the final flux through the loop, and that final flux phi b is, again, I need to know the magnetic field strength times the area of this loop. Basically, this is a circular loop pi r square, and cosine theta is maximum. This is 0 degrees, so hence field times the area, that would give me the final flux. And depending on how many number of turns, I can replace that n, and that would give me the final EMF. And hence this is what Faraday's electromagnetic law is. It's the rate of change of flux induces EMF in the wire, and hence that EMF produces the induced current in the wire. This is a simple diagram for electric generator. So if you go back in your flux equation, so you see you can induce EMF in a wire if there is rate of change of flux, right? Or if flux changes in given time. And that flux depends on the magnetic field area and the angle. So that means to change flux, I can change either of these three variables. Okay, theta, area, or magnetic field. Generally, in electric generator, what we change is the angle. So the two permanent magnets, this is just a simple example to increase the magnetic strength. There can be multiple magnets placed around it. And so here we place two magnets with north pole and facing south pole, so that the magnetic field lines go from north to south as shown here. Of course, this one has south pole to the left and north pole to the right. I'm not interested in that. We're trying to create homogeneous magnetic field lines parallel going from north to south here. And so here with the permanent bar magnet means in our flux formula BA cosine theta, our B is constant, and we take a wire loop, a square wire loop, and so that means the area of the loop is constant, right? So only thing that's changing here is angle. And how is that? The cosine theta is changing by rotating this loop there is the rotation direction with some angular speed omega, which you see as as the angular oscillation here, angular frequency. in our EMF equation here. How what the frequency of this coil rotating around um, is what is this omega is. And so again, here we're keeping the magnetic field and the area of the loop constant, but we are changing the angle. So we rotate it, and how we rotate it, again, it's a simple mechanical process. So this is a square here connected to an axle. This axle at the end can have a fan blades, so called the butterfly valves in the hydropower plants. These fan blades are hit by either water moving from the top reservoir or the steam energy from the boiling water. um, we using the coal, or we can use the nuclear rods that generate heat to boil the water. That steam energy is used to rotate these um, fan blades, and that fan blade rotates the whole coil set here in the magnetic field. So now the flux, when the coil is parallel with the magnetic field, there is no flux, because no magnetic field lines are passing through the loop. So there is zero flux when they are parallel, and when this is vertical with so the field line is going from left to right. If you have the coil going from out of the phase and into the phase, then there will be maximum magnetic flux passing through the loop. So you see the flux changed from minimum to maximum to again minimum to zero, and so on. And as that happens, the oscillating, because this thing is rotating, that produces this oscillating or the sinusoidal EMF, which in turn produces oscillating current, or alternating current, AC. And hence the generated EMF can is a function of the number of turns, the magnetic field strength, and the area, and times the rotation of this thing, which determines the frequency of the current omega, which is equal to 2 pi f, and that is equal to NBAW sine omega t. We can replace all these constants by epsilon naught, which is the peak EMF. And you can connect a wire through it with some resistance R, and V equals to IR, where that V is E naught sine omega t. Hence we can calculate I, the oscillating current, as I naught times sine omega t, where I naught is related to E naught by V equals to IR. That's again a simple generator. The next example is the mutual inductance. Uh, the magnetic field from the first primary coil will induce an EMF in a nearby secondary coil. Now, here is the first way to, produce current. If we already have some current, we can pass that current through a loop of wire or a solenoid. And if current is flowing in this loop, there is this magnetic field is induced, or magnetic field is generated around any current carrying wire. Okay, and so this blue line here is the generated or induced magnetic field by the current carrying wire. And now if we bring another set of the coils to the right hand side, very closer to the first coil, what happens? Okay, so the first set of coil produces magnetic field, and now if we place second set of coil in that magnetic field, which is like this here, what happens when we put a some conducting coils in magnetic field. If at least flux is changing, magnetic flux is changing, then current is induced. Same way, if this is a current I1, which is AC, if this is alternating current, it produces magnetic field going through the loop, and that magnetic field is also oscillating in time. And that oscillating magnetic field, which is again non-constant magnetic field, it has to be non-constant. Constant magnetic field passing through a loop would not induce current. So this is oscillating magnetic field going through second set of coil, that in turn induces EMF in the coil. This is something called the mutual inductance. We'll look this with one example in the lab today. Okay, let's move on to our lab simulations. Here's the lab for today's electromagnetic induction lab. As usual, go to this link provided here, and when you get to this page, there are two ways you can do this lab. You can download this lab here, but it will need Java installed in your laptop, and that process may get a little complicated depending on the software you have. Instead, you can run this gRPJ virtual environment for Java. Here it gives a link itself, browser compatible version here. So if you click on to this one, uh, it will run the gRPJ, and finally the lab that we're trying to do. It may take a while depending on your processor speed, internet speed. Okay, so make sure you have this program loaded with bar magnet, pickup coil, electromagnet, transformer, and generator. We'll look into all of these 5 different examples, all based on magnetism and electromagnetic induction. And since you do that, here are some simple questions on electromagnetic induction and Faraday's law and Lenz's law. Um, uh, either you can refer to simple your course book or any other physics book to answer these questions. I've answered most of them in today's lecture. And so once you open that, here are multiple questions about understanding your bar magnet. You can there are some features. You can increase the strength of the magnetic field, go up to 75%, 100%. You can flip the polarity, and you can show field lines or not show the field lines. Generating field lines help, and this is your compass that you can move around, and you see as you move the compass around, the compass needle, the red is always north, so the north is always attracted towards the south pole, and you can move along these field lines, and your compass should point exactly as the field lines of the magnet. And you can also say inside of the magnet, as I said, it's not that the field lines start at north pole and end at south pole. Magnetic field line always form a loop because there is no magnetic monopole. The magnet always comes in 2 poles. You can have one single charge, but you cannot have one single magnetic monopole, and that results in this continuous loop of magnetic field lines. And I think, yeah, with that, I mean, you'll see all these things rotating with different angles where your compass is, and you see the strength. You can decrease the strength and see, how far does that affect the compass, and so on. And so once you do the uh, magnet, so the next one is the pickup coil. It's a simple electromagnet coil, and here we can um, do few experiments that we studied today in the theory part. So we can leave the strength at 75%, or let's start at 100%. Why not? Um, so compass, I don't need to see compass. So this is a permanent bar magnet, and as we learned in the electromagnetic induction earlier, let's set the loops, and just one loop, one wire, and so these are magnetic field lines denoted by these compasses. And so as I bring the compass closer towards the bar magnet, you see these blue dots. These are the charges, you know and I mean, the compass induces EMF in the coil, and when there is EMF in the coil, or when there is potential difference in the coil, the free electrons in the wire come into that electric potential and they move, right? And the electrons always move from low potential to high potential. And so uh, so when the bar magnet is completely inside and it's at rest, the bulb does not light up. And why is that? Versus, let me move the bar magnet around to the left, to the right, and you see, whenever I am moving this bar magnet around, or whenever I'm changing the magnetic flux passing through the coil, there is induced EMF in the coil, which produces induced current, and hence the bulb lights up. But whenever the magnet is sitting there, there is flux passing through it, but that flux is not changing. There has to be rate of change of flux in order for the EMF to be induced. And I can change that by a voltmeter here. So voltmeter rates 0, and as I change the flux, you see the EMF is induced in the wire, and that voltmeter is reducing the voltage, and the polarity of the voltage switches back and forth, because as you oscillate it back, um, and once the correct current is directed one way, and the next moment the current is directed the other way, or the induced direction of induced potential changes, um, uh, back and forth. And switch back to the light bulbs. How can I increase uh, the light here, the amount of light we receive? So either I can constantly change it. So even with that, constantly changing the flux, I can change the loops. So I can have up to 3 loops for the same motion. For large number of loops, n equals to 3, the induced EMF is higher, hence the induced current is higher, and the bulb brightness significantly increases. So what's the other way to increase induced EMF? I can also change the area, right? Let's make the area 100%. So now the area is big, means more magnetic flux is passing through the loop. Flux is BA cosine theta. So hence I have much brighter light bulb. Uh, so when I move it, in horizontally along this line, that's when I have the magnetic flux passing through it. I can reduce that flux by changing the angle how the magnetic field lines passes through the area. So that goes down by theta. When theta is 0 degrees, I have the maximum flux, and as theta increases, flux decreases because cosine 90 is 0. So that means if I have a magnet down here, and if I were to flip this magnet vertical, the no magnetic flux would pass through the loop, and hence there would be no induced EMF. Okay. And the next one is the electromagnet. Uh, Similar setup here. I'm going to reduce the loop to just one for now. Electromagnet, is any metal wire or metal conductor uh, or a piece of metal that becomes magnet only when electricity is passed through it. Um, and, and that electricity can be a DC current or the AC current. For now, we are using a battery source of um, 10 volts. So, in this case, the uh, uh, the current in the wire would produce magnetic field around the loop, and you can see how the magnetic field orients around the loop. There are several examples in the book for the direction of magnetic field lines. So this with these concentric loops, or here at the origin you'd have a vertical line of magnetic field lines. And as you see, these magnetic field lines are constant in time because this is a DC source. Okay, DC source of battery provides direct current, or a current that is constant in time, that is not oscillating as the AC. So the magnetic field produced by the DC current are not oscillating, they are constant in time. You can check that by changing uh, the AC current supply here. And so instead of DC, I'm passing the AC source. So these are oscillating current shown by our oscillator here. It's doing back and forth, and I can change the frequency of it. Okay, frequency here, how many oscillations per second is what the frequency is. I can have very high frequency, that's the highest I can go. By the way, in our regular household, the current sent to us has 60 hertz. So that means the current from our outlet oscillates 60 times in 1 second. So it's quite hard to see. So I'm going to reduce the frequency here. So I see the nice oscillating graph here. I can also change the amplitude or the peak value of the current, or I naught. So here I naught is 0 versus I can get the maximum current. So what you see here is you see the flow of the electrons and the change in magnetic field directions as the current oscillates. So for the DC part, these magnetic field lines are constant because the motion of the electron is only in one direction, right? For the oscillating current, so it oscillates, it's back and forth, based on the number of frequency, and hence you see these electrons oscillate within the wire, and that you know produces the oscillating magnetic field around it. If you look at one compass needle here, or this one over here, let me bring it closer. This is the bigger one. So you see, as the current goes down versus current going up in time, your magnetic compass flips between north and south. So that means the magnetic field generated by the oscillating current around it is also oscillating. And you can change that intensity if you increase the loop, um, and versus, so frequency, all that. So what else I can do here? So same thing for the DC. By increasing the number of loops, the current through the loop is increased versus when I have only uh, one current there. Sorry, one loop over there. Uh, and so next, let's move on to the. I believe next is the generator, electric generator. Uh, so we're just applying what we have learned on the electromagnetic induction. We said we can uh, change the area. Sorry, we can change the area or the angle of it. We can change the angle of rotation of the coil by which changes the flux going through the area, and that in turn induces current in the magnetic field. So here in a generator, it's a neat example here. We will change the by turning on the tap water here. We'll change the flux uh, going through the area here. So this is our coil, and this is our magnet connected to a wheel. Each wheel like fan blades here. When water hits onto it, we can change the amount of water flowing into it. That determines the rotation of the wheel or the frequency of the wheel, and that the angular velocity of this wheel determines uh, the angular frequency or the frequency of the EMF and the current induced in the coil. And so I can increase the magnetic field strength versus lowest versus highest. So that's my highest magnetic field. I can show the point in enable the magnetic field, because that allows me to see my magnetic field lines as they change due to the compass needle here, the compass needle due to the bar magnet here. So you see magnetic field line that passes through the coil changes depending on the angular speed of this wheel here. Uh, and that I can change by amount of water that I'm passing through the magnet. So you see, as I increase the rotation, the magnetic rate of magnetic flux increases. So at one instant it's maximum 0, minimum again maximum 0 and minimum, and so on. So as this field, the it 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 fluctuates. So you see the electron is motion is in one direction at one instant and the other direction in the other instant, and that results in this, the maximum and the minimum um, brightness. So why is this flickering, and why does your household light bulb doesn't flicker like this? Again, that depends. That has to do with the frequency, and I'd like to do that as a homework. And that I will give you a little hint here. As I increase the speed, the frequency increases, and our eyes can only respond to certain frequency change, and if it's up to certain number, above certain number, then it will, our eyes cannot differentiate that frequency. Okay, and I can increase the brightness by simply increasing the loop, because that would produce higher current, versus only one loop that would decrease the brightness because of low current passing through it. Okay, and these are all the questions that you have to answer in today's lab. What else? I can try with a voltmeter here. Uh, and as you see, the voltage is oscillating between negative and positive. And if you look in the voltage graph, V naught sine omega t, that's what it's doing. It's doing the sinusoidal voltage in this format here. Okay, sorry, it was here. And I think with that takes us to the final part of the lab, to transformers. Okay, the transformers, have something, applies this concept of mutual inductance. Uh, First, we take let me put a battery source in here. So first, we take a coil and pass some current through it. Okay, here I'm passing direct current to a coil. Just one loop is easier to see, and so I'm simply connected this to a battery. Now this is my electromagnet. Electromagnet, or the current carrying wire produces magnetic field around it. If it's a loop, magnetic field lines look like this, as shown here. And so this magnetic field is constant in time. It's not oscillating. So if I bring this closer to the another coil, just a coil attached to a light bulb. So you see the magnetic field lines that are constant in time do not induce current in the wire, hence the light bulb does not light up. That's one fact, right? So there's no mutual induction here. For mutual induction, either I can, so for instance, you know, when the, when the voltage changes, goes from plus 10 to minus 10, positive to negative, I am simply changing the polarity of it. And what that does is changes magnetic field for one instant. So here you see the magnetic field is going towards left, because that's the North Pole here. And at and the next instant, the magnetic field are going outward. So the strength of magnetic field changes in the loop when I am changing the polarity. And so in that instant, I see a little flicker in the light bulb. I can increase the number of loops here, and that effect will be more visible because the light bulb brightness increases significantly. But when I stop moving, when I have a constant battery voltage, there is constant field, and hence no mutual inductance and no current through the bulb. What I can do, I can change that bulb by a AC source. Okay, now the AC source produces oscillating current, which produces oscillating magnetic field around the loop. Now as I bring closer here, I have oscillating magnetic field passing through my loop, right? And what that does is us changing magnetic field induces oscillating current in the wire. And you see the light bulb lights up. I can change the frequency. I can change the uh, peak voltage or the peak current. I already have the loops at maximum. I can change the loop area. So I increase the area, I increase the brightness. So you see, there are so many factors that's affecting the current or the brightness through the light bulb. And farther out my electromagnet is, right, my primary coil, farther out means, the magnetic field strength decreases by 1 over R. So you go farther from the primary coil, the magnetic field strength decreases, and as magnetic field decreases, the flux decreases, and hence the induced EMF decreases. So closer my coil is, better it is to produce higher amount of current. And so there are at least 6 factors here that affects the brightness. Okay, that I think I've explained, said all of them by now. But you can explore it for yourself. Let's explore how number of loop affects the brightness, the area, the uh, the peak value of the current, the frequency of the current, and how the area of the smaller or the area of the outer loop. I Here I can have a compass instead, and producing very small amount of voltage, hardly readable. As I decrease the distance, my voltage increases because magnetic field strength is directly related to the length. You increase the distance, so you decrease the distance, your magnetic field increases. Okay, with transformer, again here are multiple questions related to the transformer lab. Um, it's basically testing your basic understanding of electromagnetic induction and the factors affecting them. Okay, with that, I will stop the lecture part and let's start working on the simulation. In the transformers, uh, the n plays a big role, the number of loops. So here, if I have, uh, here I have 3 turns each, and uh, if this one produces 120 volts, right, as in our wall voltage, but our phone chargers are about 10 volts. So when you connect your phone charger, it's reading 120 volts, but its output is 12 volts because your phone can only handle maximum 10, 12 volts. So in that case, to reduce the EMF, it's taking 120 volts in the primary coil, and now as it passes EMF, as EMF is induced in the second coil, what we can do, we can reduce the area, or we can significantly reduce the number of turns, and you see the voltage has reduced. This voltage EMF here is bigger than this. I can even reduce the area, loop area. So you see the voltage has significantly reduced. Now if I want more voltage, which is called the step up transformers, if I want to increase the voltage, then I can again increase the loop area, or most importantly, increase the number of loops, and that increases the voltage through the uh, secondary coil.